Alright, so we've got a great question here dealing with a triangle with these points 0, 0, 12, 6, and 10, 0. And we have all these things to do here where we find the equations of the altitudes and the orthocenter and the centroid and the circumcenter, and then we tie it all together at the end with Euler's line. So it's a very exciting problem. But we're going to break this problem in pieces because it's a pretty involved problem. So in this video, I hope to just set up a basic graph of the triangle. Set up this triangle on a graph, find the equation of the altitudes and the orthocenter. In the next video, we'll look at the centroid, circumcenter, and Euler's line. Now, before I really get into this video and problem here, I want to just point out that what's so exciting about all of this to me is that what we're really looking at here, what we're really examining are different types of centers of a triangle. And I think this is neat because triangles, if I said to you, where is the middle of a triangle, it turns out there are so many ways to answer. So I mean, even on a simple level, if I set up a triangle, right, and I said, oh, where's the middle of this triangle? How would you do that? Well, one thing you might do is, okay, look at the vertices here, and then, okay, let me just drop an altitude to each side. So we'll drop a line here at a 90-degree angle to the other side. Right? Right there. One here. And then one here. And of course, this is called the orthocenter. Well, that's one type of center of a triangle. So there's my orthocenter. And maybe you feel like you found the center. Well, I said, well, no, I mean, I want you to be able to find the middle as if you're trying to balance this shape on your finger. Like, where would you put your finger on this shape to balance it? Oh, okay, well, now we'd find the centroid. And what's that? What's an entirely different type of center? With the centroid, you connect the middle point of a side to the opposite vertices. So we're going to go from, let's say, this point right here. Try to find a good color. This point right here to here. And we draw a line there. And we'll draw a bunch of these. We'll go from this middle to about here, to this vertice. And this middle to the other side. And now all of a sudden we get this other point. And that's our centroid. Wow, cool. Okay, so it's another type of center. But this keeps going, right? The circumcenter has a whole different idea attached to it. The circumcenter says, okay, just draw a perpendicular bisector to a side. So cut the side in half and draw a line at a 90-degree angle. So for this side down here, it would be about, right, a line going through the same median as with the centroid, but at a 90-degree angle. With this yellow line right here. And then with this line, right, over here, at a 90-degree angle, we come down, like this. And with this line over here, right, maybe it's a little bit more like this. So now, and this is a rough sketch, of course, we meet at this point. And now we've got a new center called a circumcenter, where we bisect each side, but with a perpendicular line. And notice these lines don't go back to the vertices. But anyway, they have 1, 2, 3 types of center. Circumcenter, a centroid, and an orthocenter. And this investigation is so cool because there's just so many other types of centers to examine. And what's so neat about these 3 points, and we'll find out pretty soon, and we'll verify this, Euler discovered that these 3 points will always be on a line, right? They'll always form a line. So if I was to travel from the orthocenter through the centroid and the circumcenter, this blue line, which you might be able to see, let me fix it. This blue line right here, which is called Euler's line, is the line that all the points are actually on. So Euler's line will always tie these together, and no matter how weird your triangle is, you'll find that these 3 types of centers are on that line. So let's get a start on this problem. Like I said, we're going to graph this and look at the altitudes and orthocenter. And we're going to confirm that these centers are different, but they are all on the same line, which is really fascinating. So let's get started. Scroll down a little bit. Now I don't have a line tool here. So you have to assume that we have a y-axis right here on this line. Let's say this is our y-axis, and here's our x-axis. I'll just set up a little start of the grid. Okay. And over on the x, And there we go. Okay, so of course that's a mini grid, but we'll still use that as a reference point. So we have point A over here, and let me use blue for that. A is at 0, 0. B is at 6, 12, so 2, 4, 6, 2, 4, 6, 8, 10, 12. And I'm just assigning these values. I mean, A could have been 6, 12. There's no given value. I'm just going to pick an arbitrary point. And then C is at 10, 0. So 2, 4, 6, 8, 10. Right here. This is C. It's at 10, 0. Now, this is our triangle. I'm going to roughly connect these with dashed line, because every time I try and draw a straight line, it ends up being dramatically curved and looking quite awful. So here's my attempt at a straight line. All right, dashed line. Oh boy. So you keep, there, fix this. All right, there's our triangle. All right, so our first job is to find the equation of the altitudes of this triangle. And altitude, again, it crosses through a vertice, and then it will cross the opposite side at a 90-degree angle. So if this green line right here is our first altitude, I know it's going to cross AC at a 90-degree angle. So this is really helpful, right? We know it's going to cross a 90-degree angle, so if I find the slope, right, of AB, so the slope of, AC, this line down here, that's just delta y over delta x. So I'm going to do 0 minus 0, which is 0, over anything, in this case 10 minus 0, or 10, is 0. So this line is perpendicular to that. And what do we know? Well, a perpendicular line, the perpendicular of slope AC, it's my shorthand, is going to be equal to the negative reciprocal of 0, except you can't flip 0 over, because then you'd be dividing by 0, right? It's just 0 over anything. We don't know what's over anything. The reciprocal of that would be, well, x, anything over 0, and that's undefined. You can't divide by 0. So this slope is undefined, and you might think, oh, I'm supposed to find the equation of this line, but it's undefined. What do I do? Well, this is actually a nice and simple problem at this point, because this vertical line, all vertical lines are of the form x equals something, because this line's going up and down, has all these y values, but only one x value. And you know the x value. It's right here in this point. This point's telling you it has to cross at 6. So that means this equation for this line is just x equals 6, right? Because it's at this vertical line crossing through 6. So that's nice and easy. So x equals 6, and that's for, we'll call that altitude B, because it crosses, right? It crosses the vertex B, altitude B. All right, 2 more to go, and we're on our way. So now let's try altitude A. Again, altitude A is going to start at this vertice over here, and it's going to travel over to the opposite side, right? Starting here, it's going to cross this side at a 90-degree angle, so maybe rough estimate, something like that. All right. So now, how do we deal with this problem? Well, I'm going to use, I love using slope-intercept form. Right, y equals mx plus b. mx plus b. And this is great in this case because we know as a cross point A. Point A is on this altitude, and A is at 0, 0. And that's our y-intercept. So we know b equals 0, and the slope is only one step away. It has to be the negative reciprocal of the slope of this line of BC. So we find the slope of BC, right, delta y over delta x. So delta y up at 12 minus 0, or 12, over 6 minus 10. 6 minus 10 is negative 4. So the slope of BC is negative 3. But the perpendicular bisector has a perpendicular slope to BC. It's the negative reciprocal. So we're taking the negative of negative 3. Well, negative of a negative is a positive. It's not 3 over 1, it's 1 over 3. So the slope of this line is 1/3. So using my slope-intercept form, I'm going to say that altitude, right, A has a slope of 1/3, so it's y equals 1/3 times x, And I could have it 1/3 times x plus 0 because the y-intercept is 0, but I'll leave it as this right here. So we have our second altitude. And we've got one more to go for the altitudes. So what do? Well, next we have altitude C. Again, it's going to start here, it's going to cross the other side at a right angle, and it's going to meet the other two altitudes here. We'll get to that point in a moment. That's our orthocenter. And this one, I guess, is the toughest, but we can deal with it. I'm going to use y equals mx plus b form. And again, first I'm going to find the slope of AB, because I know I need a negative reciprocal of that. Delta y, 12 minus 0 is 12. 6 minus 0 is 6. That's 12 over 6, which is 2. The perpendicular slope of AB is just going to be what? Well, the negative of 2 is negative, and then 1/2, negative reciprocal. So, one more step, right? We know this altitude has to cross this vertex. That's 10, 0. That means that the point 10, 0 is on this line. And we could use the point slope form here, but I love my slope intercept form. So what do? I'm going to plug this point into our equation. This is our x value, and this is our y value. I'm going to plug this point in, right, with the slope to solve for the y-intercept. So what does that mean? Well, instead of y, I'm going to write 0. So at this point, y equals 0. Instead of mx, I'm going to write negative 1/2, that's our slope, times our x, which is 10, right, plus b, right, that's our line. Now I'm going to solve for b. So negative 1/2 times 10 is negative 5, plus b equals 0. Add 5 to both sides, and that's our y-intercept. So the altitude C, right, what does that equal? Well, that's y equals negative 1/2 x plus 5, and that's our third altitude. So now we don't need to, I guess, but we want to find this point. Where do these things meet? Well, that's called the orthocenter. And the orthocenter is just going to be the meeting point of our three equations. So we have them here. So what we could do is set equations equal to each other in some way to solve. But what I might want to do is just use the fact that I know already this point has to be at 6 blank something, because the line x equals 6 has to have an x value of 6, so we're already getting started. So let me just clear off some of this. Alright, so what do? Well, again, we know x has to equal 6. So what's so nice about this, actually, is that at all of these lines are equal at one point at the orthocenter. So, and all of these lines have an x value of 6. So just by plugging in a value of x equals 6 into any of these equations, right, we'll get the y value. Now, altitude B isn't very helpful, right? We already know x equals 6. Altitude C has a fraction in it. I'm going to use altitude A, right? Altitude A is y equals 1/3 times x. Well, x is equal to 6 here. We know that. And y is equal to 1/3 of 6, or 2. What does that mean? Well, that means that at this point, if you plug in 6, you get 2. So the orthocenter is 6, 2, right? That's where the lines meet. And that's our first center of our triangle. So we've taken care of the equation for the altitudes, and we found the orthocenter. In the next video, we'll look at the centroid, circumcenter, and Euler's line. Alright, thanks.